able to. He got his PhD in 2015, then moved to Berkeley, was at Berkeley for 4 years, is currently still at CERN, I'm told, or working at CERN, although he's in Milan at the moment.
Yeah.
He has he's going to be an assistant professor in Milan from the end of this year.
All right, thanks. Thanks, Will, and thanks everybody for showing up, even remotely. So today I would like to talk with you about the few results we had on primordial non-Gaussianities and of their observational signature in the large-scale structure over the last couple of years. And just to set up the stage for everybody, we know that nowadays we have a cosmological model which works pretty well. There are some glitches. One of them is not shown in this plot, is this H-naught tension. But generally, everything is pretty much consistent with each other, both measurements of the CMB and isotropies between different experiments, expansion rate, and comparison between the BAO and the CMB, and measurements of the growth structure between, also the comparison between the CMB and galaxy surveys. So what all these data give us is this lambda CM model, which has different ingredients. Some of them are the energy densities. And so these are dark energy, dark matter baryons, neutrinos, and photons. But on the same footage in terms of importance for the success of this model in predicting observations are the initial conditions of this model, which are pretty special. So we know that they have to be nearly adiabatic, scale invariant, and approximately Gaussian. So what I would like to introduce briefly, so yes, let me say this one thing, which is because I think is important before we move on. And it's a statement that now that we have this model that we know it works so well, even it's just wrong, and we will break it in some way, maybe H-naught or maybe something else. Otherwise, it's important that when we look at the next generation cosmological observatories, or CMB, or galaxy, or 21 centimeters, it's important that we focus on those parameters from which we can actually learn something. And so it's not really important if we measure the baryon density or the dark matter density 10 times better, if this doesn't bring us more knowledge about something. So the parameters which are, where there are benchmarks, are those for which we do have some theory prior. And so those are, for example, the inflationary ones, neutrino masses, number of degrees of freedom, curvature, tensor mode, and so on and so forth. And so today I would like to focus on one of them, which is the amplitude of primordial non-Gaussianities. I would like to tell you one recent data analysis that we did using EBOS data in collaboration with Will and others. And then an idea that we had also to try to improve over these measurements in the future, where the DESI data will become available. So this is the outline, as I just told you. So why we are so obsessed with these initial conditions, and why we think that inflation is a very good candidate to provide dynamically the initial conditions for our universe. So inflation tells us that a large scales were actually causally connected in the past, even though they were not at the time of CMB last scattering, and that's why there is this huge homogeneity of the temperature and isotropy on very, very large scales. It tells us that the universe is flat, it's close to flat, unobservably flat, and this is the 2 sigma bound from Planck plus BAO. It also tells us that the initial perturbations are almost scale invariant, and they actually have to be slightly less. So scale invariant is approximately broken, and so the tilt of the initial primordial fluctuations has to be less than 1, and it's measured to be 0.96, and it's different than 1 at more than 10 sigma, more or less now. Fluctuations are adiabatic, which is also something very peculiar, because it tells us that every field had the same initial value of fluctuations at early times. And also it makes some predictions for the tensor modes, which have not been observed yet, and also tells us something about the Gaussianity of the fluctuations, whether or not we can actually observe them, or we are talking mostly about the free theory, where all fluctuations are Gaussian. So of course, if we want to say, okay, let's study non-Gaussianity, there is many ways in which primordial fluctuations can be non-Gaussian. And so rather than going at this by looking at specific model and computing the amount of expected non-Gaussianities and compare these models with the data. It's always better if we have some guidance from the theory and we have some results which are model independent. Sorry. So for one particular case, we do have model independent results, and this is the case of the squeeze limit of endpoint correlation function. And now here I'm focusing only on the simplest one of them, which is the bispectrum of the curvature perturbation zeta. So in the squeeze limit, which is the limit in which one of the K modes, K1, is much longer than the other two. So the K1 is much smaller, so the wavelength is much longer than the other two. There is a theorem by Maldacena more or less 20 years ago and generalized by Paolo Creminelli and Mattia Zaldariaga, which says that the bispectrum in this configuration in single feed inflation, single clock inflation, regardless of the content of the Lagrangian, is zero, is basically unobservable. And so it's a very powerful statement because it tells us that if we do observe the bispectrum in the squeeze limit, then we can automatically exclude all possible single feed model of inflation. And so how do we go about this? It's possible to show that for the squeeze limit, the curvature perturbation can be parameterized in a local form. So when you have the curvature perturbation zeta, which is the sum of a Gaussian piece and a quadratic piece, which is local in space. This is why they are called local non-Gaussianities. And so the target here is to constrain this parameter FNL, which tells us the amplitude of promoted non-Gaussianities to order 1. Because this is more or less the value that models which are not single field will predict. And so even if we do have a non-detection, we'll be able to say something about the fine-tuning of these multi-field models. So far, the best way to constrain promoted non-Gaussianities has been the CMB. So you take a CMB map with FNL equals 0, and then you compare it with a theory map where you actually put FNL. And so here I'm just gonna show you one with FNL 0, one with FNL 10. You can see they're nearly identical. Nonetheless, Planck has been able to put these extremely tight constraints. So FNL is 0, and the uncertainty is about 5. So it's still far from these theoretical uncertainties of order 1, but it's getting there. It is slowly getting there. But let me just pause for 1 second, and if you don't think that this CMB constraint is remarkable, so let me just say that this is the best measured parameter in cosmology, other than the temperature of the CMB. Because if you now look back at this expression of the curvature perturbation, we put some value from about 10 to the minus 5. What we know is that our universe is Gaussian in a part with precision of 0.05%. So these extremely accurate measurements of the Gaussianity of the universe, although not enough. So CMB is going to improve a bit in the future, especially with small scale, with terrestrial experiment that can measure the polarization of the CMB up to high L in the cosmic variant regime, which was not possible with Planck. And so we would like to back it up with something, and this something are the large-scale structure of the universe, which nowadays are still far. The uncertainty is about 25, but I'm going to show you, and I hope to convince you that in the future, this could be actually much better. Oh, let me just say that although I know there is a protocol to raise hands in the chat, if you have something to ask, it's also okay just to unmute yourself and ask a question. So the first part is going to be about the data analysis that we did last year. And so before we discuss the data analysis, it's important that we understand what is the observable we're talking about here. Because in the CMB, we said that we need to look at the bispectrum of temperature and isotropies. And so for galaxy, it turns out that there is actually an observable in the 2-point function. And so let me just guide you through the argument. So we know that the galaxy fluctuations is a very complicated function, and we certainly do not have an exact analytical solution, neither numerical. For that, what we do is that we rely on the so-called Pigberg-Ground split, which says that if we look at the fluctuations of the galaxy field on scales much larger than the single galaxy, we can treat the problem perturbatively and expand in a series of operators which we think are relevant to discuss our problem. And these operators are always are set by the symmetries. It's not that we can choose one and drop others. We need to put everything that is consistent with rotational invariance, translational invariance, and equivalence principle. And so if you look at this equation down here, I wrote all the three linear operators that you can write, but in fact, it turns out that if you assume equivalence principle and the universe is Gaussian, you cannot write the first two. Because of course, the first two will just correspond to the bare value of the gravitational potential, which we know is not observable, and the gradient of phi is just an acceleration. So what you would do is just go into the elevator and free fall, and you will not see the effect of this operator. So in a Gaussian universe where the equivalence principle is respected, the relation between the underlying galaxy density field and the underlying dark matter field needs to start with this operator delta m, multiplied by an unknown coefficient v1. And so what changes is now that if you have primordial non-Gaussianities, but you still keep all the symmetries, is the following. Now we said that the gravitational potential of the curvature perturbation has a nonlinear piece. And this nonlinear piece is actually pretty important because now let's do the splitting that we discussed in the previous slide between long wavelength and small wavelength and compute the gravitational potential phi in a theory where you have primordial non-Gaussianities. What you see is that just by doing the series expansion, that there is this new term, which is a coupling, which is the product, if you want, between the long wavelength phi long and the short wavelength phi short. And this is, of course, only non-zero if FNL is non-zero, because this just tells you that long wavelength gravitational potential cannot affect the dynamics of small scales, because you can always do different transformation and get rid of it if FNL was zero. So this is in fact what's going to play the role of the observable now in the galaxy power spectrum. And so just to remind you, the relation between the gravitational potential and the density fluctuation is through the Poisson equation. And so phi is proportional to delta with a proportionality constant alpha, which scales with k to the -2, where k is the wave number. So now let's try to repeat the same argument for the bias and see if something has changed now that we have this nonlinear term in phi. So the variance of the small scales, this delta x squared short, or average over the short modes, which we call sigma, now is affected by the variance by the presence of the long wavelength mode phi. And so it's rescaled to 1 + 2 times FNL phi long. What that means is that when we define the bias, this unknown coefficient, which is nothing else than the response of the galaxy field to the presence of the long wavelength mode, now you pick up an extra term. So there is this first one here, and then there is an extra contribution, which is proportional to FNL, which is nothing else than the change of the number density of objects with this local rescaling of the small scale variance of the modes because of the presence of primordial non-Gaussianities. And so this was first realized by Neil Dalal, I don't know if it's connected, and others by more than 10 years ago. And it tells us something which is very important, that for galaxies, for nonlinear structure, there is a signature of primordial non-Gaussianities even in the 2-point function. So we do not have to go to the 3-point function to see a signal. So as we were saying, this scales with alpha, which is nothing else than Poisson equation. And so what we do expect is that if we look at this bias on very, very large scales, K wave numbers much smaller than the quality scale, then this bias will pick up a term which is proportional to k to the -2. So this has been measured extensively in simulation and tested. So we know pretty well what's going on. This is just the results of a simulation from Nico mouse almost 10 years ago. And you can see that if they run a simulation with this FNL plus or minus 100, they see k to the -2, sorry, scale-dependent bias at very low k. The only thing which I didn't tell you is what is the value of this B5, because this is a number which is also unknown. And so either you have some theory prior, or the only thing that you can constrain in your data is the combination of FNL times B5. We do actually think we understand something about this B5. using both simulation and analytical arguments from Biggs theory. And more or less, what is true is that what happens is that this B phi is a number proportional to the bias of the tracer itself. So here you see a formula which says that B phi is a number times B minus 1 or B minus another number. And this has been shown to be accurate to 10–20%. So we're going to stick to some of these results in what follows. But let me just add that although we can only, in principle, constrain the product of these two, we only care about detecting FNL, because if we detect, we can exclude already all possible single field model of inflation. So it's not really important the value, it's much more important if we detect it or we don't detect it. So let's just look at the power spectrum now with the presence of Primordial non-Gaussianities. So you see here in red, this is the standard case. And in blue, this is the sort of theoretical benchmark of FNL of 1 that you would like to measure. So there's two main issues in trying to do that. The first one is cosmic variance. And then the second one is, so this is what cosmic variance will look like for something like DESI. So pretty bad. So naively, it looks like it's going to be very, very hard to detect FNL of 1. On top of that, at very low K, there are other observations fact that come into play, which are related to selections effect, photometry, and other various systematics that we have to take into account. So this is not going to be easy, but it's important that we try to do our best. And so what we did last year was to take the EBOS data, which has some advantages in constraining Primordial non-Gaussianities, but also some disadvantages, as I will show you. And we try to do an optimal analysis, and we obtain the best constraints on FNL using large-scale structured data. So what is this optimal that I'm referring to? So usually when we try to see how good an experiment is before we actually take the data, is we use a Fisher matrix approach. Of course, when you compare with the numbers that you got from the Fisher and your actual data, they are never close to each other. And this is for various reasons, because of course there are many simplifying assumptions that go into the Fisher matrix. But on the other hand, there is also, it's also important that the Fisher matrix automatically assumes that you're doing a statistically optimal analysis of your data. Whereas this is not obviously not always what we do in the data. In fact, it's not what we do. We almost never do it. And so this is already going to be a source of discrepancy between our Fisher expectation and what we actually do in the data. So over the last 5 years, there was people have started to think again about this problem in terms of, can we optimize statistically our analysis technique in order to get the best constraints from for things like the BAO, resist-space distortions. And recently we also thought about doing this for FNL. And so how do we do it? Let me just tell you what is the philosophy and what we expect to find. So what do we know about primordial non-Gaussianities? We know that they are primordial. So we do know that phi does not evolve with time. And this is something that you can see by comparing these two terms here in this expression. So you have the standard term, which is proportional to the dark matter density, which is a function of redshift. And then you have phi, which is not a function of redshift, because this is not the dynamical effect that can be generated by general relativity, but it has to be there from the beginning in the initial conditions. This Gaussian piece in particular decreases with time. This is just the growth of structure. And also at high redshift, we know we do have more volume. So naively, what you would do in order to do the optimal or the best possible analysis is that do not bin your data, because you're looking at very large scales. So if you do not want to bin your data and not account for the cross correlation within the different redshift bins. And also, given this fact, we also want to give more weight to the galaxies which are further away from us than the ones which are closer to us, because that's where the primordial non-Gaussianity signal is the largest. So technically, there is just one simple way to do it, which is to write down an optical quadratic estimator. And so given a set of galaxy position, delta at x1 and x2, you just need to build this estimator, which is nothing else than the sum over the galaxy position x1, x2, weighted by the inverse covariance, and then multiplied by the response of the covariance to the presence of FNL. This is really easy to do, and automatically it tells you that you need to measure the power spectrum, which we hope, which we knew is what we're going to do. And it also tells us that before you do the Fourier transform of your data to measure the power spectrum, you need to weight your data in a special way. And so the weights are written down here. And so you see the first thing that you want to do is trivially that you want to upweight your galaxy by the response to FNL. So you want to upweight them by B phi of Z. And that's important because since the bias is usually a growing function of redshift, this weight is going to give much more importance to the galaxy at high redshift. And at the same time, we said that we want to downweight the Gaussian piece. And so technically what happens is that you need to multiply the Gaussian piece by the growth of function, d of z, which is a decreasing function of time. So this is exactly what these two sets of weight, one for the monopole and one for the quadrupole, are going to do for us. Whereas in the standard way of measuring the power spectrum, you set all these weights to 1. And so I'm going to refer this to the standard case as FKP analysis by the Feldman, Kaiser, and Peacock-Paver that set this up. Of course, there are weights in the FKP, but those are not signal weights for FNL. So, so let's see how this would work for a survey like EBOS in this case. So the data release 14 of EBOS is consists of 180,000 quasars in the redshift range between 0.8 and 2.2. There are many more quasars at lower redshift and higher redshift, but we have not been able to analyze them yet because of systematics. The number density is pretty low. So this means that this is not exactly the best sample you would use to test an optimal estimator which minimizes sample variance, because here basically every mode is going to be dominated by short noise rather than by cosmic variance. It's a small fraction of the sky, it's about 5%, but still, because it's very extended in volume, is about 10 gigaparsec. So it's a lot of volume. And there are two separate patches, North Galactic Cap and South Galactic Cap. And the people in the EBOS team have done an amazing job in trying to remove the contamination at low K, and we find almost no contamination. They will find a bit, and I'm going to discuss, I'm going to say a few words about it, but basically we do not find any systematics at low K that would generate a very large positive FNL measurement. So what we're going to do is to just run our optimal estimator on this EBOS sample and see if we can improve over the standard analysis. So this is in plots. What I just said is the number density is pretty low. It's about 2 times 10 to the minus 5. And so this is sort of a scary plot that tells you that basically all the modes are going to be dominated by the short noise, which is this red line here. So for this sample, the weights look like this, as this plot here on the right. So you see this weight, W tilde, which is the one that upweights galaxy by their response. I'm going to show you in 2 different lines, because I said that this is a number proportional to the bias, but there is an additive constant which we don't know very well. We think it's a number between 1 and 1.6. It could be anywhere in between. So we are just going to do the analysis in both cases and show the results in both cases. And so these are the 2 response weights which take into account the response to FNL. And then there was the part which was downweighting of the Gaussian signal. So we were expecting these W0 and W2 to actually go down with redshift. They do not pretty much, and they do not because the product of D of Z times B of Z, then it's almost a constant and slightly increasing function of redshift. So this is so what we are learning is that if we want to do if we want to constrain Primordial Non-Gaussianity, it's always best to select a sample where dz times b of z is a decreasing function of redshift. And this is not always the case, but for instance, it will be the case if one day 21 centimeter cosmology becomes reality. So for something like EBOS, what do we expect? What do we expect in terms of the improvement? So you see here on this plot, we just run a simple Fisher forecast for the error bars on FNL as a function of Kmax, which is the smallest scale included in analysis, and for different values of Kmin, which is the largest scale included in analysis, because we didn't know if we could include all of them or not because of systematics effect. So what you should compare is the continuous line and the dashed one, where for the same color, where the dashed one is the standard analysis and the continuous one is our optimal analysis. Generically, we find improvement about 20%, which means that for free, just by reweighting our data in a smart way, effectively, this means that we just made the survey 4 times larger, and we provided 40% larger, and we provided 40% more quasars. So this is really, in terms of money that you would save, if you had to go and get all those spectra, it actually means a lot. So we do expect a 20 to 20% improvement. So these are the measurements. And by eye, you cannot see that the error bars on the power spectrum are actually getting any smaller. So here on the left, you see the standard analysis FKP. This is just for the Southern Galactic Cap. And then there's the optimal weighting of the data and the corresponding monopole power spectrum for the case where this constant P is set to 1 and when it's set to 1.6, which is sort of the range where we expect this response to be.
Emanuele, we have a question from Nayesh. Nayesh,
oh, yeah, sorry, I didn't see. Yep.
That's okay. So I was just wondering, you said that EBOS team have done a great job by making sure that this redshift range you looked at doesn't have any contamination, but how do you distinguish contamination from an actual FNL?
Right, no, this is the $1 million question, yes. Let's say that since we know that Planck has set this very strong bound, and we do not expect EBOS to be constraining at that level of accuracy, that was okay. In the future, this is going to be a huge problem, because how do you know if there is really FNL of 1 in your data and you're just removing it because you don't think there should be any? So in the future, this is going to be a huge problem.
Okay.
That, likely we didn't have to deal with yet here, but it's going to be very important in the future. And I think there is a lot of people that are pushing, in fact, to do sort of blind analysis and try to use some of these techniques, not to have a bias when we try to make these measurements. Of course, I was saying that there is no significant bias at low K. In fact, there is a very large one in the quadrupole that we couldn't, and this is why we could not use the quadrupole in this analysis. On the other hand, when we do primordial Non-Gaussianities, usually the shape of the power spectrum is fixed. So you're keeping all the other parameters fixed. When you make these measurements, or you take a Planck prior. So this means that effectively the quadrupole is not bringing any information.
Okay,
so this is one case where we do find that our optimal analysis improves a lot. So this is the posterior for, if we compare, if we fit for FNL in this panel on the left and in this one on the right, and they are shown in red and blue. And so we see that in fact the optimal analysis the posterior for FNL is much sharper. And in this case, we do find more or less a 40% improvement for this specific case. If we combine everything together, things are not as good as this specific case. And so for P equal 1, we do find 50% improvement. So we have not been able to reach the Fisher value even with the optimal analysis. And this could be due to small residual systematics. It could be due to other effects that we didn't take into account, about, for instance, integral constraint or other subtleties in the window function. But still, of course, the posterior are very non-Gaussian, so it's even hard to make the comparison. But if you now look at these 95% credible intervals on the left and on the right, you will find that the optimal one is 50% narrower than the other. And so this is the best constraint using large-scale structured data alone, not in combination in the CMB, with the CMB. And it's only, let me just say, only 7 times worse than the CMB. And it's only 7 times. I'm gonna discuss this briefly because the future actually looks very bright. Because now we have taken quasars, we already have quasars at high redshift. And so already by including those, we should be able to get down to FNL of 10. So this is just almost a factor of 2 improvement if you can include the quasars all the way up to redshift 3.5. Compared to, to this release that I was discussing with you, we also now have more area. It's almost more or less a factor of 3. So you can now rescale by the square root of this number. And what you will find is that EBOS quasars alone, in principle, the full sample could yield constraints which are comparable with Planck. And this is spectacular because we know that Planck is basically, at least in temperature, full sky cosmic variance limited experiment. And we could, in principle, do as good as Planck with 50% of the sky of super noisy data. So this tells you the power of spectroscopic data and in general of galaxy surveys when we try to constrain non-Gaussianities. There's one thing that I would like to mention that although this improvement didn't seem too large, 15 to 20%, this was because the quasars were completely short noise dominated. What we've checked is that for something like Euclid or TESI, for the samples where you have more galaxies like ELGs or H-alpha galaxies, then the improvements would be much larger. So now I'm going to move to the second part of the talk. So maybe if people have questions now, it's a good time to ask.
I had a quick question. So this is just using galaxy positions, right? Via the bias.
Yes.
I mean, if you look at two-dimensional clustering, you know, redshift and projected, can you not get something more out of that? Because you can get something out of that locally, but I don't know whether you could get something out of that at high redshift.
No, in general, the redshift space does not help a lot. In fact, basically, 99% of the information is in the monopole. And what happens is that velocities are completely unaffected by primordial non-Gaussianities because of the
that's sort of what I was wondering. So I was wondering, could you not use that to sort of constrain, you know, what the, I mean, in effect, constrain what the non-Gaussian bit should be, or sorry, what the Gaussian bit should be relative to the non-Gaussian, for instance, constraining, you know, just what the galaxy bias is in the case of no non-Gaussian.
I didn't hear you, the last part of the sentence.
Oh, sorry, just constraining what, you know, for instance, the galaxy bias and the galaxy distribution is in ignoring non-Gaussianity, right? Or comparing the two, in effect.
Yes, yeah, but more or less, this is in practice, this is what we're doing, because we're taking summary statistics of this distribution, in this case, the power spectrum. So we're really just comparing the bias, in fact, at the level of the power spectrum, not the level of the full galaxy distribution. And we're doing this in redshift space. So using the monopole only because we couldn't use the quadrupole. But if I understand your question, this is more or less what we've been doing already.
Okay.
And so you mentioned, you know, like, so you mentioned that the quadrupole was not usable. Like, what was the reason, Emanuele?
So the quadrupole, well, we don't know. Unfortunately, with systematics, you never know. So we tried our best. There was a lot of back and forth between us and Ashley, Ross, and other people, but it wasn't clear what was going on with the quadrupole. But I can tell you that the quadrupole only would like an FNL of order 100 in order to fit the data. And in fact, you know, in some sense, it's good that this was not showing up as large in the quadrupole, in the monopole. But it was a huge problem in the quadrupole.
It was a problem on large scales in the quadrupole.
Yes.
Yeah.
So how do you know this is not a problem with the monopole?
No, we don't. As I was saying, we don't. We just know that since FNL is already constrained very strongly by by the CMB, we didn't see detection of FNL much larger than the CMB bound. This sort of tells us that, okay, the monopole is fine. Whether in the monopole, in this data, there is an FNL of 5 or there is a systematics, I don't know. I have no way to tell you now. But these are all the things which are gonna haunt us in the future, for sure. Okay, should I move on?
Carry on, yeah.
Yeah, okay. So the last bit of the talk, how much time do I have?
Another 20 minutes.
Okay, so the last part of the talk is more about like a more speculative idea, which is why maybe to measure primordial non-Gaussianities, it's better to see nothing rather than something. And so we would like to make the case for tracers which have actually zero clustering on very large scales. And so why this is interesting? Because as I was saying before, in the limit where B goes to 0, the power spectrum itself goes to 0. So having a 0 signal, it's actually something very weird, because if you take any luminosity or mass selected sample, this will never happen. So you always plateau to some very low but positive infinite value of the clustering. So what this means is that if this zero bias tracer exists, it must be something else which is not the mass luminosity selected sample. So and why we were interested in this is, again, going back to the plot I was showing you early on about cosmic variance. And so because we really would like to get rid of all these cosmic variance at very low K, which is nothing else than the fact that we can only measure one realization of our universe. So the cosmic variance affects us very, very bad, because it tells us that no matter how many billions of dollars you put in your telescope to see more galaxies, the constraint will never improve. So what you see here on this plot is the error on FNL as a function of the number density of galaxies for a tracer of bias 2. So you see that basically as soon as you hit the sort of 10 to the minus 4 number density, then you don't gain anything by measuring more galaxies. And that's because the error bars on these very large scales are completely dominated by cosmic variance and not by the short noise. So how do we go about it? What Uroš did more than 10 years ago was a rewriting of ideas about the likelihood that were already around, and notice that if you now have two tracers and have very low short noise, then you can play the following game. So imagine that you have, where's my cursor here? Imagine that you have a sample which in blue of bias 1.5, and this is fluctuating because of cosmic variance in the volume. And then you have in the same part of the sky another tracer which has a higher clustering, but it has to fluctuate in the same way because you observe them in the same patch of the sky. So what that means, if you now imagine that you take the ratio, which you never want to do, you never want to take ratios of random variable, but just think, let's imagine that we can do it. So now imagine that the noise is very small. What this means is that we can cancel the stochastic part of the dark matter density field and just measure the deterministic part of this relation, which is the bias. And so what this means is that in principle, by using cross correlation, we do not have to pay the price of cosmic variance twice. And we could measure FNL much, much better getting rid of it. Of course, nobody has been able to show in practice that this works, that you can combine two tracers in the same area of the sky and improve on FNL. So this is more of, so this has to be taken with a grain of salt. Recently, people have been discussed the possibility that the CMB lensing or the CMB, the KSZ effect could act as the second tracer. And so there are interesting ideas by Marcel and Uroš and Matt, I don't know if he's online, about how to do that. But even in that case, it's hard to do FNL of 1, even if you have two tracers. And so what we did was, this is just to show you how this would look like. As soon as you, with the multi-tracer, you improve, but you really need to go to very, very very large number densities. So it still doesn't look like this would be feasible just with tracers, just with different galaxy samples. So let's just go back to why this cosmic variance is an issue. And the curse here is that in our universe, the error on the measurements is proportional to the measurement itself. This is the statement about cosmic variance. So if we try to measure this power spectrum in redshift space, there is a piece which is as the signal and there is the noise. And if you compute the covariance of this measurement, this is proportional to the signal itself, plus a tri-spectrum. And since we are focusing on very large scales, I'm going to neglect this tri-spectrum, but you see what the problem is, that we are trying to measure something, but then the error is proportional to this something that we're trying to measure. But for FNN, there is something special that happens, which is that now we actually do not care at all about the Gaussian part of the signal. It's just noise for us as well. So the idea is that if we could just set the signal part of the covariance to 0, then we would only be left with the short noise. And so in this case, this tracer will have 0 signal, which it's easier to detect the deviations from it, and its covariance will only contain the term which is proportional to the short noise. So this actually helps quite a bit. And this is just the same Fisher forecast as before. And what you see is that by comparing the dashed line and the continuous one, that for two tracers which have the same signal, it's always better to take the one with the lowest value of the bias because that one has the lowest noise. Of course, zero bias, it's nice in principle, but in practice, how do we find such a tracer? And so it's important when we do it to keep in mind a few things. This is something that we should actually be able to do it in the data, otherwise this would be a completely academic exercise. It's important that there is enough galaxies after we do this selection, because otherwise the noise would be too high. And we should also take into account the fact that this is an nonlinear transformation. So Andre, Neil, and Will and others have looked at the fact that nonlinear transformation generates velocity bias. So this is something that we also have to take into account. And so these are a number of constraints that we would like to follow in order to define the tracer. Voids are a possibility because it has been shown even in BOSS data that there exists a sample of voids which has zero bias, but those are too sparse. The number density is about 10 to the minus 5. So it rescues us just a very simple classical mechanic example. And so imagine that we do have a galaxy here in the upper corner, and we want to compute the force between this guy here and a bunch of galaxies which are very far away from it, the distance d. And let's imagine that these other galaxies are arranged in a small part of the sky of size L. So what we know is that if this distance is much larger than the size of this area, we can just compute the force as if all the galaxies were in the center of mass and just put all the mass in the center. But now imagine just for the sake of the argument that these galaxies are arranged uniformly in this patch. What this means is that this galaxy far away will not feel any force, because from very far away, it will look to this galaxy that this region of space is empty. Whereas of course, as soon as it gets closer, it will realize that there is actually stuff in it. But from very far away, this region of space will look empty. So what we need to do is to find all the regions which look like this and compute their clustering. This is basically what we want to do. We want to take the galaxy field and define all these different regions such that when we compute the power spectrum of these regions on scales much larger than the size of the region, the power spectrum will be 0. And it's interesting to show, I'm not going to go into the details here, but you can actually get rid of all this mambo jumbo, which I just said, and do the full excursion set sort of peaks theory calculation and show that this would actually be the case. So just quickly, what happens is that when you try to calculate what is the value of this bias, it's usually a number of order 1 divided by the variance of the small scale fluctuation sigma squared. And here I'm doing a sum over different scales because we don't know what are the important scales for deformations of a galaxy or for the selection of a particular sample. So one scale is, of course, the halo or galaxy scale. This is what I call R peak. And now if we want to make this selection such that this environmental scale, this L, is much larger than the scale of the halo or the galaxies. And so it just happens that in our universe, where the power spectrum is a certain power law, the variance of the fluctuations at scale R peak is much larger than the variance of the scale on scale RE. And so since the bias is inversely proportional to this quantity, what happens is that basically at the end of the day, the bias is going to be proportional to the value of the density field on the environmental scale divided by the variance of the field on the environmental scale. And this has been checked also in simulation to work pretty accurately. But it actually has been checked to work in data. So these are real data. This is in the Sloan main sample. This is from Shadab, Lam et al. And Sim Paranjab et al. More or less two years ago. So here you see the following. So they measured the galaxy bias as a function of the density in spheres of 8 megaparsec around each galaxy. So what happened is that if you go to the 25% lowest percentile, and you look at either the auto or the cross, so the auto is just the auto of the galaxy, and the cross has been done using lensing with the photometric catalog. So what you see is that basically there is a sample which is about 25% of the galaxy for which the clustering is 0. So it's interesting just to say, to repeat this, that 25% of the galaxies in Sloan main sample have 0 bias when they're selected in this particular way. And there's nothing fancy about this because in fact they have been able to reproduce the same trend using the MOCs when they had HODs, which were not trained to reproduce any of these measurements. So that was just a standard HOD, which was luminosity dependent. So we just repeated the same thing, not on data yet, we did it on a simulation. So what we do is that we set a threshold delta. We set it on some scale. We set 8 megaparsec, but we try many different others. And then we divide halos accordingly to the density around them, whether it's larger or smaller than these threshold values. So the ones which sit in regions where the environmental density is larger than this threshold, we call them the high bias sample. The ones which sit in density in regions lower than this threshold is the low bias sample. And then we just measure the bias of them as a function of K. So this is what you see here in this plot. So basically you go from an underdense region, which had bias of -1, you keep going, and then at some point you cross 0, and you go to overdense regions. But of course, it's important to notice that the bias is flat and 0 only on very large scales, because as our example before on classical mechanics, when you go to small scale, you start to see that these regions are actually not homogeneous and the clustering is not 0. So we did a bunch of other measurements. So we can measure the bias as a function of the value of this environmental density defined for the halos themselves, not for the dark matter, because unfortunately dark matter, 3D dark matter is unobservable. For different halo masses, we can find how many of these halos are there. And so for instance, we find that when the bias is 0, depending on the halo mass, we go between 20 and 45% of the halos. So high mass halos, sorry, the other way around. If we have more halos, there is actually a larger fraction of them which would have 0 bias. And we also computed this number B5, which is the response, and that's what we need to put into our forecast. So just visually, I'm not very good at visuals, but this is my stab at it. So this was the original distribution of halos in the simulation. And so this is the distribution of, this is how when we split them, the yellow ones, of course, doesn't look at all like homogeneous, but when you measure the clustering on very large scales, it will be 0. So this is my last slide. So we then decided to just run this through a simple feature forecast. So we said we took some numbers which are in the ballpark of what the DESI sample could look like. So I mean, redshift about 1 and total volume around 50 gigaparsec. This was a bit optimistic maybe. We marginalized over a bunch of other parameters, and that's what we find. So this is the error on FNL as a function of the number density, and the DESI are sitting around here. And so what you see in blue is the standard analysis, where it never gets below a number which is over the 3 or 5. Whereas in our case, we're actually being able to push this much, much closer to 1 with improvements which are more or less a factor of 3. If it's important that if we could make this environmental scale smaller, the improvement would be even larger, because it would be even more scales where these fields look homogeneous. But of course, here then you run in issues about the noise, and so we could not do this for 6 megaparsec for all the possible number densities. But in general, what we find is that improvement are about 3 times compared to the standard case. So this is my last slide, and then there will be a final summary. So the message here is that if you have a fixed number of galaxies, you want to minimize cosmic variance. And if you cannot split in different samples, and there's no effective way to do this nowadays, we can actually use other information, which is contained in the sample itself, for instance, the environment. And this is something that people looking at the environmental dependence of galaxy formation have already did in the data. And we just exploited the same argument to show that this would work also for primordial Non-Gaussianities, and in principle improve error bars by a factor of 3. And there's something which we started doing right now, which is just download the BOSS data and try to do this ourselves now on BOSS rather than the slow main sample. So this is my conclusion. So in the future, we will know if we do have a detection of primordial Non-Gaussianities or if we do not have such a detection. But in both cases, if we can go down to this threshold of FNL of order 1, we will be sure that we have learned something. Although to get there, we need new ideas and new methods. And I discussed one of them, one of both. So one is the optimal analysis of the EBOS sample, which is designed to get us closer to what is the Fisher matrix of the same data telling us. And we do find 15 to 20% improvement, which is not a lot, but it's a good starting point. And of course, there is a lot of that needs to be done. So similar to what happened in the CMB, we need to extend this to the bispectrum, because eventually at some point we'll also measure the bispectrum of the galaxy clustering. And also then I would discuss a more speculative idea, but which we think has a lot of promise in improving our constraints on primordial Non-Gaussianities. And this relies on the idea that zero bias is the simplest way with a simple tracer to minimize cosmic variance. And this improves more or less by a factor of 3. Standard analysis, and there's something which is going on that we're checking this in some mocks that we got from some people in Euclid. So just the summary, and this is all I had to say. Thank you very much for listening.
That was great. Thank you very much for that really nice talk. Do we have other questions? We've had a few in the middle. Any questions specifically on zero bias tracer part?
I have a question. Is this really different from like a 3-point function or biospectrum analysis?
It is, yes. It is in the sense that some of this will be certainly contained in the bispectrum, because we know, in fact, that the bispectrum is the first statistic that tells you something about the distribution of your sample, right? We did it this way because although the bispectrum will contain some of these, it's not obvious if the bispectrum will be able to exploit the bispectrum fully in the next generation of galaxy server because of poor understanding of the modeling or the systematics. Whereas for the power spectrum, we sort of have a better handle. So in some way, this is one trick to bring some of that information back into the power spectrum. But in principle, if you could measure all endpoint function, you would never do something like this.
No, but I guess this particular thing you're talking about, that you're looking at the environment of the galaxies and then pick, I guess, the ones with where the environment is neither overdense or underdense. Is that what you're saying? I guess I'm still not quite clear on.
Yes.
Zero bias. So what sort of endpoint function is that looking at?
Well, I don't have a definite answer. For sure, a lot of is looking into the biospectrum. But it's also the statement that you, at the same time, you're minimizing cosmic variance, which is not something you would do if you just measured the bispectrum itself. Because the bispectrum maybe would improve by 50% over what over the power spectrum, not by a factor of 3. So it's like putting the bispectrum, but at the same time minimizing this issue of the cosmic variance.
Okay. Okay. Interesting. Thanks.
Other questions?
Well, to follow up on that, I mean, like, right, like, you know, so your method sounds like you're like pixelizing like space, and then you're selecting the pixels that are a certain density, and then measuring like the large scale clustering of those pixels. Like, is that a valid way to think about it?
It's a good way to think about it. We're not really taking pixels because we are selecting galaxy. So because around each, so we take a galaxy into our 0 bias sample if the density around it is some specific value close to 0, close to homogeneity. But you can think of these as pixelizing the space on the environmental scale and look at some selection of these pixels. Yes.
Right. Okay. And then you're looking then at the large scale 2-point clustering, basically of those selected regions.
Yes.
And so if you didn't just take like 2 subsets, but instead just use like all of the pixels, you know.
Yes. Yes. There is of course, yes. This is a very good question, because naively you will not do what I just said. So this is just something that we found that works, and it's interesting and it's easy. But in principle, what you would do is that you take all these pixels and you find some weight which is density dependent, which brings the best final constraint. That you will not fudge with all this sampling and splitting. If you just have all the pixels and you want to minimize cosmic variance, you just have to find the density dependent weight which does that for you.
Mm-hmm.
We just did the super simple thing of splitting in 2, and that's it.
Right. No. Yeah. I understand. Yeah. Like, I was trying to think through like what would be the optimal way of getting those weights. Like, you know, was the effect just to change the PDF of the density? And so then like the signal you would be looking for, I guess, is like the deviation from a Gaussian PDF of those densities in the pixels.
I think, yes, you can also, you can do it at the level of a 1-point statistics as well, yes. I don't know how, I don't know how robust that would be, but I think you could do that, yes. The way I would do it more formally is to just write a marked correlation function or marked power spectrum.
Mm-hmm.
The same way people do when you want to constrain modify gravity. You just want to have density dependent weights because you want to select regions where there is screening, or which regions which are unscreened. So I would do a marked statistics, which is density, where the weights are density dependent.
Mm-hmm. Interesting. Okay, thanks. Yeah.
Okay, any last questions? Okay, well, let's thank Emanuele again, remotely, as we do.
Thanks, Emanuele. Very nice talk.
Thank you.